right, this is section 6.3, page 3. We've got another example here. We have AD is 10. Let's go ahead and label that. AD is 10. That's 10. And we know that BC is 4. Let's label that one. BC is 4. And we know that AE is 7. So AE equals 7. That's this guy here. Okay. All right. So now what we're thinking of is it sort of looks like the last problem, but there is a difference. In the last problem, we had two chords that intersected, and we had all the little pieces of those chords that intersected, except for one. Well, that's not the case here. We have, this chord that's not intersecting with that chord at all. So we've got to go about this a little differently. Well, what I didn't explain to you before, because I knew we were going to get to this problem, is that the way that result came about was through similar triangles. So what we're going to be able to show is that if we can show that these two triangles are similar, then we'll know their sides are in proportion, and we'll be able to come up with an equation that'll help us solve this. So let's do that. Let's see, can we prove the triangles similar? Well, to begin with, and when I say triangles, I mean these two triangles here, okay? To begin with, don't we know that this angle here and this angle here are congruent? Because they are vertical angles, right? Okay, so the first thing we're going to say is angle AED is congruent to angle CEB. Okay, so that's our first piece. Now, can we show that any other angles are congruent? Well, I want you to notice that if we take a look at angle A, what do we know that it is? Well, it's an inscribed angle here, right? Because its vertex is on the circle. So it's going to be half of its intercepted arc. So if we draw that out, its arc will be DB. Now notice angle C is also an inscribed angle, and it will be equal to half of the measure of its intercepted arc. So what is its intercepted arc? Well, DB. So they both intercept DB. That means they have to be congruent. Remember, we had a theorem that said that. If they both have the same intercepted arc, then they're congruent. What we're going to say is we're going to say that the measure of angle DAE, that's this one right here, is equal to 1/2 the measure of that arc, DB. And we're also going to say that the measure of angle DCB is equal to 1/2 the measure of that arc, DB. Okay, well, these things together mean that the measure of angle DAE is equal to the measure of angle DCB, or angle DAE is congruent to angle DCB. So now we can say this one is congruent to that one. Well, isn't that going to be, that's our second little dot there? That tells us the triangles are congruent by AA. So, or not congruent, I'm sorry, similar. So we can conclude that triangle DAE is similar to triangle. Now be careful here. We want A and C to match up and E to match up. So that must mean D and B. D, C. I'm sorry. We want DAE, right? And then BCE. There we go. Okay, those are similar by AA. Okay, so then we know the sides have to be in proportion. Okay, so their sides are in proportion. Okay, so if we do big triangle over little triangle, big triangle over little triangle, then what do we have? We have this side, DA. What does that correspond with? Well, DA corresponds with BC in the little triangle. And then I want to use this side. We're using the sides we know the length of. AE over, now what does that correspond to in the little triangle? Well, if we look back here, AE corresponds to the last two, CE. Okay, so then we put the values in. DA is 10, BC is 4, AE is 7, and CE is what we're trying to find. Actually, they call it EC, so I'm going to turn it around and call it EC. Okay, so how do we solve this? Well, we're going to cross multiply. Let's go ahead and write 10 over 4 equals 7 over EC. So we're going to cross multiply here. So what do we get? We get 4 times 7 is 28 equals 10 times EC. We divide both sides by 10, and we get that EC is equal to 2.8. And that's our answer for that problem. Okay, a little bit of terminology now. BC here is called the internal segment of the segment AC, and that's because it's inside the circle. AB is called the external segment of this whole segment AC. Okay, we needed that to be able to do this theorem. If two secant segments are drawn to a circle from an external point, so let's go ahead and do that. Let's draw two external, so secants are supposed to cross twice, so we're going to go like this, okay, and then another secant, so we'll say something like, I don't know, let's make it not look like it's the same here. Okay, so those are from, this is our external point, okay, then the products of the lengths, so we need to label all this. Let's label this, so we're going to say A, B, C, and we'll call this D and E. Okay, so if two segments are drawn to a circle from an external point, we've got that, then the products of the length of each secant with its external segments are equal. Okay, so first of all, let's talk about what are the external segments. Well, on this one right here, the external segment would be the one outside the circle, CB. And what's the other external segment? This one here, CD. What would the internal segments be? The ones inside the circle, so BA and DE. Okay, so now we're trying to come up with a formula. It says the products of the length, so we're not going to want any bars, we want the length of each segment. So the length of the segment, so this is the length of the segment, that would be CA, times what? Times its external segment, so CB. Okay, that's equal to the length of the whole thing, CE, times the external part, CD. Okay, and this all comes from similar triangles. All right, let's try this in the problem below. We're told that AC is 12, so the whole length is 12. So I'm going to go ahead and denote that like this. The whole thing is 12. And then AB, this part right here, is just 6. Okay? And then we know AE is equal to 14. Okay? So now they ask us a question. They want to know what is AD. So our question is, what is AD? Okay, well, that is taking into consideration this theorem here. So we know that since they're both secants drawn from an external point, we should be able to say this piece times the whole thing is equal to the external times the whole thing. So we're going to say AB times AC, so the external times the whole thing. I know I'm reversing the order here, it doesn't matter. External times the whole thing equals external times the whole thing. So AD times DE. All right, so what do we get there? Well, we plug in, what is AB? 6. What is AC? 12. What is AD? That we don't know, so we're going to just write AD. And what is DE? 14. So 6 times 12 is 72 equals AD times 14, or let's call it 14 AD. 14 AD. And then we're going to divide both sides by 14. And what do we get here? We get that AD is equal to, let's see, there's a 2 in there, so we get 36 over 7. 72 divided by 14. So divided by 2 is going to give us that AD is equal to 36 over 7. Or if we use a calculator, what are we going to get? We get 36 divided by 7 equals, say like this, 5.1428 on forever. Okay, and we'll say or. All right, that concludes page 3.